Okay, Assalamu alaikum warahmatullahi. Good morning. Okay, Assalamu alaikum warahmatullahi. Good morning, good afternoon, good evening, wherever you are. I welcome all participants to the technical session 3 of the Icoget, and the track for this particular presentation is petroleum exploration and production operations. So my name is Aliyu Adebayo Suleiman. I will be chairing the session for this afternoon. So without much further ado, I think let's just go straight to the business of the day. We have 7 papers today, and I hope all the presenters are ready. So I'm going to call on the first presenter for today. He is Hazam Baham from University Technology Petronas, and the title of his presentation is Palynofacies Analysis and its Application in the Evaluation of Source Rock, a Case Study, Mountain Formation, Northeast British Columbia, Canada. So over to you, Hazam.
Hi everyone, my topic is about balenofacies analysis and its application in evaluation of source rock, a case study, mountain formation, Northeast British Columbia. Let's at the beginning talk about the balenofacies. Balenofacies is defined as the studying of organic matter, aggregates, especially palenomorphs, and relates them to the depositional environment and hydrocarbon potentiality. Petrophysicists, geochemists, and reservoir engineers rely heavily on the quantitative and the qualitative properties of shale gas rock, the dispersed organic matter derived from the different sources of marine and non-marine forms the focus of analysis of petroleum geologists. Balenofacies analysis is an effective way to assess the thermal maturity. The changes in color of organic constituents as a cause of heat change the extents from diagenesis to metagenesis phases, which corresponds to the thermal alteration index. The purpose of this study is to evaluate the corrosion type and degree of thermal maturation using geochemical and petrographical methods, and link the results of thermal alteration index to the geochemical ones. As for the study area is located at the northeastern part of British Columbia, Canada. We can notice here from the map the approximate location of the involved wells. Mountain formation is a multi-layered accumulation of fine-grained sediments, shale, silt, sandstone. From the Triassic age, it was deposited in the offshore to shore face environment. The mountain formation considered to be an important hydrocarbon reservoir in Western Canada since the 1950s, as it was the target of oil and gas exploration by the National Energy Board of Canada by 2005, and with the occurrence of horizontal drilling and fracturing techniques, unconventional mountain clay was the main gas reservoir for the British Columbia Oil Gas Commission. Materials and methods, 42 samples or 42 core samples were obtained from the two wells. Each sample was crushed and divided into two parts. The first was used for the pyrolysis using the source rock analyzer, and the second part was used to balenofacies analysis using the standard process of balenofacies extraction proposed by Stablin 1982. The results of the source rock analyzer or pyrolysis are listed, as you can see in table 1, in which that the main parameters of TOC, S1, S2, and S3, and Tmax were obtained. A descriptive analysis was done for these parameters. As we can see, the minimum of the TOC is 0.5 and the maximum is 3.2 weight percent. For the S1, it ranges from 0 to 6.39. The S2 from 0.04 to 0.189, while the Tmax result falls between 442 to 465 Celsius. We can notice here that the results of the S1 and the results in the pyrolysis results are higher than S2 in most of the samples. The calculated parameters of hydrogen index and oxygen index and production index reveals a very low content of hydrogen index and oxygen index and a high relatively production index. The use of organic methods to assess thermal maturity gave results almost consistent with those of geochemistry. The overall organic constituents and the studied slides show a dark brown to very dark color metals, as we can see in figure 2A, B, C, and D. Samples from well B65J contained plenty of very dark brown phytoclast and black opaques with frequent very dark brown degraded phytoclast as shown in figure 4A, 2A and B. Paleomorphs particles were not observed frequently. There were some paleomorph fragments, but could not be confirmed due to their high degradation and very dark color. Hence, they were considered as phytoclasts. Phytoclasts and opaque particles of the equal size were much more common than lath-shaped ones, especially in the well B65J. Depending on the results of the pyrolysis, the organic richness of the and hydrocarbon potential of the analyzed samples show a fair to good source rock, as we can see from the cross plot between S1 and TOC. Also, a cross plot of HI and Tmax were established to determine the kerogene type and maturity, which shows that the kerogene type almostly is in the type 4, with some samples in the type 3. We can see also that all the samples of the well B65J is in the type 4, while the other well, the samples are divided into two, between the type 4 and type 3. Another way to determine the maturity is plotting Tmax with BI. We can notice that most of the samples are falling in the, or all the samples are falling in the post-mature dry gas window. Also, we can notice that there are non-indigenous hydrocarbons, which may explain why the S1 is higher than the S2 in the pyrolysis results. And the use of palinophages to determine the maturity. We can notice that most of the phytoclasts are in dark color. So as a criteria to assess these phytoclasts, this criteria was suggested by Fisher, Pearson, Staplin, and Yutting. We can place these phytoclasts on the 3 and above thermal alteration index, as we can see in this graph. By the combination of the parameters of maturity, we can see that all the samples are laid in the late mature to the over mature area. We can see here the line, the green line of the thermal alteration index shows that the samples are in the post-mature stage. As for the conclusions, the following conclusions were obtained from this study. The TOC richness in the studied wells shows a fair to good source rock, and the generating potential is in the gas window. Kerogene type 4 was the main type identified from nearly all studied samples. The analyzed samples from well B93I likely initially contained kerogene type 3 that transformed into type 4 during the process of thermal maturation. The observed pyrenofacious samples indicated a high level of maturation, which denotes that the organic matter has already generated the hydrocarbons corresponding to their kerogene type. Finally, comparing the results of the geochemical analysis with TAI shows a high similarity with which makes the pyrenofacious analysis considered to be an effective, fast, and cheap procedure for evaluating source rock. Thank you. Okay. Anyone there? If there
Yeah, Mr. Hazam, can you hear me now?
Yes, I hear you.
Okay, good. Thank you very much for your nice presentation. So let me now check whether you have questions for you. Okay, there seems to be no question, but in the meantime, let me just seek some clarification. Can you possibly just tell us how you confirm the reliability of TAI for highly mature source rock? Because since you compare your results with the geochemical results, and for highly mature source rock, you said that the geochemical results are often imprecise. So how can you convince us that your method of TAI because you use the TAI. So how do you confirm the reliability of your result for highly matured source rock?
Okay, thank you for your question. For the reliability, I didn't say exactly that the geochemical methods are not precise, but in the highly mature formations or source rocks, the results of the geochemical analysis may have some inaccuracy. There is some reliable results in highly mature source rocks, especially our case. Our case is mountain formation, and this formation is highly mature. So we rely on the palynofacies because it will give us more precise results if we can use it in proper way. So it needs an experience, a good experience, to determine the color of the palynofacies exactly. If you can determine the color of the palynofacies or palynomorphs exactly, this will give you a good results and the precise results about the source rock maturation.
Okay, thank you very much for the response. Actually, the question came, as a result of what I read in your abstract, because your abstract actually states that the geochemical results in the highly mature source rocks are often imprecise. So that was why I asked that question, actually.
Yes, you are right. You are right. You are right. For the highly matured rocks or source rocks, the geochemical results sometimes gives imprecise results. Also, if there is results like I said in my presentation that the S1 is greater than the S2, which means that so this will cause some problems in the geochemical results.
Okay. Thank you very much for your response, Mr. Hazam. So we really appreciate your presentation today. So I think that's about all for the first presentation. Thank you again, Mr. Hazam. Our next presenter is...
Thank you very much.
Thank you. Thank you. Our next presenter is Kasaulia Tamalmani. The title of our presentation is The Study of Oil Palm Biomass Performance as Green Corrosion Inhibitor for Oil and Gas Application. So I'll open the floor for Kasaulia for our presentation. So over to you, Kasaulia.
Good day to the panel of examiners. I am Kausalya Tamilmani from University of Technology Petronas, Malaysia. Today I'll be presenting on the study of oil palm biomass performance as green corrosion inhibitor for oil and gas application. The content of my today's presentation will be introduction, problem statement objective, scope of study, literature review, methodology, results and discussion, and finally the conclusion. Moving to the first content, introduction. Corrosion has always been an issue among all the industries, especially the oil and gas industry. Though there are various applications of oil and gas, yet pipeline transportation has been a significant application in the industries. Regarding this, the safety of the oil and gas pipeline operation has become concerned since pipelines are constantly exposed to threats. Anyhow, to tackle this issue, the use of corrosion inhibitors were introduced in the industry, where usually the conventional, which is the chemical-based corrosion inhibitors, will be utilized. However, concerning the environment, the green corrosion inhibitors like plants and fruits were proposed as an alternative starting in 1990s. The use of biomass-based as corrosion inhibitors were also studied more or less than 10 years. This is because the biomass waste is produced in Malaysia in huge quantities are often left on the plantation to retain its nutrient for the sand and to become the mulch. Hence, for this research, the biomass waste like empty fruit bunch and also oil palm frond were used. Moving to the second content, problem statement and objectives. The main problem statement faced during this research is the corrosion. Corrosion has always been the major setback in the oil and gas industry. In order to confront this issue, the use of conventional, which is the chemical-based corrosion inhibitors, were introduced. However, this use of chemical coercion inhibitors has resulted in new problems such as toxicity. Hence, the problem statement of this study was focused on whether the biomass-based can be used as green coercion inhibitors as an alternative to encounter the coercion issue. Comprehending the problem statement, three objectives were targeted for this research. First, to evaluate the performance and effectiveness of empty fruit bunch powder and the oil palm frond powder as coercion inhibitor for the rate of coercion. Secondly, to determine the inhibition efficiency of empty fruit bunch powder and oil palm frond powder by examining the emission time and concentration of the inhibitors. And lastly, to analyze the surface morphology of the metal surface in the absence and presence of empty fruit bunch powder and oil palm frond powder as coercion inhibitors. Moving to the next content, the scope of study. The parameters tested in this research was concentration of inhibitors and also the emission time. As for the concentration of inhibitors, 25, 50, 100, 150, 200, and 250 ppm of concentration of inhibitors were used. And for the emission time, 72, 168, 360, 480, and 720 hours were tested, which is from 3 to 30 days. The experiments conducted throughout this research were weight loss measurement, adsorption isotherm, and testings like FTIR and also SEM. The material used for this research was copper, alloy steel, hydrochloric acid, conventional inhibitor 5CI5, and also the biomass waste such as empty fruit bunch powder and oil palm frond powder. The literature review of this research was mainly focused on coercion inhibitor, and oil palm biomass. A comprehensive literature were done concerning on the mechanism, sources, and chemical process of the coercion, aspects conventional and green coercion inhibitors, as well as the recent research related to the project and also the chemical composition of the oil palm frond and also empty fruit bunch as per the oil palm biomass. Moving to the next content, which is the methodology. This shows the overall flow of the research which I conducted. The first stage and the second stage, I used different type of metal, which is first the copper and second is the alloy steel. The alloy steel was given to me by my supervisor, and it is the alloy steel which is commonly used in the oil and gas industry for the pipeline. The material used for this research, as I stated in scope of study, which is the hydrochloric acid, CI5, conventional inhibitor 5, empty fruit bunch powder, and oil palm frond powder. And the experiments and testings which were conducted throughout this research is the weight loss measurement, adsorption isotherm, FTIR, and also SEM. And with this, I would continue with my next slide, which is the results and discussion. This graph over here shows the rate of coercion with and without the oil palm frond and inhibition efficiency achieved by the oil palm frond powder. It was apparent that the rate of coercion increased with the time. Regardless, with the presence of oil palm frond powder, the rate of coercion was observed to decrease with increasing concentration of oil palm frond powder. The maximum inhibition efficiency achieved by the oil palm frond powder was 99% with 250 ppm concentration at 368 hours, which is also the reason why the rate of coercion is maximized as 360. This is because the rate of coercion was increasing gradually until 360 hours, but started increasing drastically thereafter. Similar results were achieved for the empty fruit bunch powder as well. Maximum inhibition efficiency attained by the empty fruit bunch powder was 99%, but not at 250 ppm like oil palm frond powder, but this is much lesser, which is at 100 ppm powder itself. Next, this is the CI5 result. The reason I used the CI5 is only for comparison purpose. I wanted to compare whether the biomass-based rate of coercion and inhibition efficiency can be similar to the conventional, which is the chemical coercion inhibitor. And yes, it was proven with these graphs that the rate of coercion increased with increasing immersion time and decreased with increasing concentration of the CI5, and the maximum inhibition efficiency attained by the chemical is 100%, where the biomass-based attained 99%, which has proven itself to be a good green coercion inhibitor. With this weight loss measurement, it was clear that the empty fruit bunch powder and oil palm frond powder can perform as green coercion inhibitor. Moving to the next slide, which is the FTIR result, in both oil palm frond powder and empty fruit bunch powder, the hydroxyl group, the OH group, was found to be the dominant, followed by the carbon-hydrogen chain and also carbon-carbon chain. These functional groups were known to inherit the inhibiting traits based on the previous works of literatures. Not only that, the heteroatoms present like the oxygen, the carbon, the hydrogen, which are found in this oil palm frond powder and empty fruit bunch powder, are also known to be a part of cellulose, which aids in the inhibition of metal surface based on previous literatures. As it can be seen here, a similar functional group can be seen for the Ci5. With this, it can be said that the functional groups and heteroatoms present in the oil palm frond, empty fruit bunch, and Ci5, they contain the inhibitory traits, which is another reason why this biomass waste can be used as corrosion inhibitor, as an alternative for the chemical corrosion inhibitor. Next, the adsorption isotome was studied. The linear coefficient values, which is the R square value of the Langmuir, attained the closest unity of 1 compared to the other two adsorption. This value were plotted in these graphs are actual value plotted based on the formula given. Hence, if we were to compare with the predicted value where a 45-degree line over here, it can be derived that closer the points to the 45-degree line, the higher the value of R square is, which also indicates the goodness of the fitness. Hence, based on the R square values of the predicted versus the actual, it can be said that this study obeyed the Langmuir adsorption, assuming a monolayer adsorption. Moreover, the value of K and the Gibbs energy obtained for the before that, I would like to show all three. This was obtained by the empty fruit bunch powder, this was obtained by the oil palm frond powder, and this was obtained by the Ci5, where all three show similarity of R square equals to 1, R square equals to 1, and R square equals to 1 for the Langmuir. Now talking on the value of K and the Gibbs energy obtained for the Langmuir isotome for empty fruit punch was 39.45 liter per gram and negative 18.87 kilojoule per mole. As for the oil palm frond, the K value obtained was 38.69 liter per gram and negative 18.83 kilojoule per mole. The value of K actually indicates the effectiveness of the inhibitor molecule adsorption, where the value of K obtained for the empty fruit bunch and also the oil palm frond powder proves a strong inhibitor molecule adsorption on the metal surface and good inhibition efficiency. And the value of Gibbs energy obtained for both of these, they were close to negative 20 kilojoule per mole, which indicated a physical adsorption. Lastly, talking on the scanning electron microscope, the metal surface of inhibited raw copper. Please note that these scratches visible on the metal were due to the graded grit paper. This image is before the immersion in the acid. It never even immersed. It's a raw copper. And this is after it's immersed in the hydrochloric acid without the presence of oil palm frond and also the empty fruit bunch as corrosion inhibitor. These show all the surface morphologies of the copper with the presence of oil palm frond powder. There is an improvement in the surface morphology where the surface of the metal can be seen attaining a smoother surface as the concentration of the oil palm frond powder increases with the lesser damage and peaks. The least damage and smoother surface are noticed during 200 ppm and 250 ppm, where this statement agrees with the quantitative result obtained where the highest inhibition efficiency was attained during 250 ppm of concentration. This clearly is due to the presence of the oil palm frond powder inhibitor on the surface that aided in to reduce the corrosion rate. On the other hand, the metal which were immersed in the hydrochloric acid with the presence of empty fruit punch powder showed more or less similar result like oil palm frond powder. The damage of the surface is significantly reduced when the concentration of inhibitor increases. The concentration of 100 ppm depicts the best surface compared to the others, where this result corresponds to the highest inhibition efficiency obtained during the weight loss approach at 100 ppm concentration. These images are evidence where the passive film existing on the metal surface inhibiting the active sites according to the previous work of literature. And finally, for the conclusion, both the oil palm frond powder and empty fruit punch powder have successfully attained 99% of inhibition efficiency at concentration of 250 ppm and 100 ppm within a period of 360 hours. The hydroxyl groups, they are known to inherit the inhibiting property, which are found in both the oil palm frond and also the empty fruit punch powder. Langmuir adsorption was elected to be the most suitable adsorption since the highest R-square value 1 was attained at 360 hours for empty fruit punch powder and oil palm frond powder. As for surface morphologies, the damage, the roughness, the pitting reduced as the concentration of inhibitor increased. And finally, with this research, I would like to conclude that the oil palm frond and empty fruit punch powder can be used as the green corrosion inhibitors as an alternative of the chemical-based corrosion inhibitors. With this, I would like to end my presentation. Thank you. Is there any question that you would like to ask me?
Yes, please. Thank you very much for the presentation, Kasoya, for a very job well done.
Thank you,
So
sir.
let me check if we have questions for you from the audience.
Right, sir. Sure.
Okay, so while we still waiting for some questions from the audience, let me just ask you, um, under what corrosive environment did the inhibitors actually achieve 99% efficiency? I'm talking about the pH. So under what pH value did you achieve the 99% efficiency?
Actually, sir, I never really conducted any test on the pH value because like I had enough time to do in these parameters and my testings. So I never really had time to work on my pH because I had to do my toxicity test and everything. So I never had time because also it was COVID and all the labs was closed during that time. So I couldn't really focus on doing on pH. But if there's a chance for me to continue my PhD or something regarding this topic again, I'll definitely test. I'll keep this question in mind. So I'll do it. I'll work
Okay,
on the pH.
okay. Okay, now, which of the two inhibitors actually achieved the 99%? Is it both of them or just one of them?
Both of them, but empty fruit bunch achieved a higher inhibition value with lower concentration compared to OPF. So I think oil palm frond needed more concentration, higher concentration to achieve 99, but empty fruit bunch achieved it in much lower concentration.
Okay, so and how do you see the possibility of these inhibitors being used in the oil and gas industry? Do you think they actually stand a very good chance of being used as inhibitors?
As for my personal opinion, so yes, when I doing this, we never really worked on this industry side to be applied in the field to test and see. Yes, but then I think we should really try to move this towards industry because since now most of the companies is moving towards green corrosion, green environment based. So I think using green corrosion inhibitor would be a very good choice, which would also won't harm the aquatic animals and all. So I think in the future, nearing future, we should try to implement this in the industry. So if there's a chance for me to actually do it, I will definitely try to bring this to the industry, experiment work on this.
Good, good. Thank you very much, Kasoya, for the presentation and for
Thank you.
the informative presentation.
Thank you.
So I really appreciate that. So I wish you the very best of luck. So thank you.
Thank you, sir.
Now, we now move to the next presenter. She is Nur Hadira Halim from Flow Assurance and Formation Damage Group of Petronas Research in Malaysia. The title of our presentation is Development of Dual Function Demulsifier by Evaluating Relationship of Demulsifier Properties with Crude Oil Characteristics. So over to you, Nur Hadira Halim.
Assalamualaikum, a very good day to all the speakers as well as participants in this Icoget conference. I'm Nur Hadira Halim from Petronas Research Sdn Bhd. I'd like to present to you on our technology research findings entitled Development of Dual Function Demulsifier by Evaluating Relationship of Demulsifier Properties with Crude Characteristics. So what motivates us to come up with this technology? Treatment of produced emulsion is a major challenge in the upstream petroleum industry. Most common demulsification method is the application of demulsifier chemical, since this demulsifier chemicals is more economical compared to mechanical separation. So bottle test is used to analyze the performance of demulsifier in resolving this emulsion. However, these tests are time consuming since we need a lot of demulsifiers to be tested in the demulsifier test kit. So this test is quite time extensive. So it is very beneficial to have a selection guideline of the demulsification prediction to cut short or expedite the demulsifier selection process for faster remediation strategies. So let me brief you a little bit of theory of demulsifier properties. First is the relative solubility number. It is actually an empirical determined value to characterize water solubility and hydrophobic hydrophilic character of your demulsifier surfactant. It is commonly used to characterize demulsifier or emulsifier. A demulsifier with RSN less than 13 is considered insoluble in water, while RSN more than 17 are soluble in water or water soluble. Effective demulsifier to treat water in oil emulsion mostly have high RSN, which is water soluble type of demulsifier. For this study, we only covered two types of demulsifier chemical group, which are resin alkoxylate and modified polyol. From our study, resin alkoxylate is a fast water dropper and it is the most versatile demulsifier for covering all treating aspects, where we use this demulsifier as a major portion inside our demulsifier formulation. And the other group is the modified polyol, which its benefit is destabilizes water in oil emulsion since it has dewatering and desalting capabilities. Okay, this is the list of demulsifiers that we use to test in our study, which is about 16 demulsifiers altogether, ranges from RSN 11 to RSN 21. The molecular weight is ranges from lesser than 5,000 to the highest amount of 50,000. As for the test matrix, it covers 4 types of synthetic crude, ranges from API 27 to API 40, and we tested it at 2 different temperatures, at lower temperature, which is 35 degrees C, and higher temperature of 60 degrees C. And we can see that we were varying the stabilizing agent of asphaltene, solid, and wax to see the effect of this stabilizing agent into your emulsion behavior in your demulsification behavior. After we conducted all those demulsification tests via bottle test, we managed to determine the relationship between the RSN to different type of emulsion producing from a different various kind of asphaltene, solid, and wax content. First is the impact of the temperature. We can see that demulsifier performance, I put the laser pointer here. Demulsifier performance is decreasing at 35 degrees C, especially for crude API 37, whereby this API 37, it has the highest wax content. So that's why wax has impact to the temperature. So at lower temperature, demulsifier performance is decreasing. For low wax content of API 34 and API 40 crude, demulsifier RSN still maintain working at high efficiency even at lower temperature. Now is the effect of wax content. We have found out that demulsifier with RSN 19 works for wax content 6% and below, but for higher wax content, the demulsifier needs higher RSN for it to work, which is at RSN 21. On the effect of asphaltene content, we have found out that for high asphaltene content condition, which is more than 1.2%, demulsifier RSN work the best, but for low asphaltene content of lesser than 1.2%, demulsifier RSN work the best. And lastly, with the effect of solid content, for heavy crude of API 37, 1 out of 2 demulsifier of RSN work best for all solid content amount. For light crude, demulsifier worked at RSN 19 and RSN 20 for solid content of lesser than 1%. For higher solid content, RSN 21 worked the best. Now, we come up with the relationship of the demulsifier chemistry to different type of emulsion. Here, we segregate between the effect of no presence of solid and with presence of solid. With no presence of solid, we can see that resin alkoxylate type is better in dehydrating the crude compared to modified polyol. But when you have solid in your crude, it seems that your modified polyol is a better demulsifier compared to resin alkoxylate for a low API crude condition. But for high API crude condition, we can see that the performance are comparable between these two chemistry group. After we have developed the demulsifier relationship, now we can use this guideline and apply it in this workflow. So we start from determination of the crude properties and process temperature of your crude, and then we select the base demulsifiers from the recommended RSN from the guideline. And then we still need to conduct the bottle test by dosing 100 ppm of the proposed base demulsifiers from step 2 into the crude oil mixture. After that, we need to see at least, is there at least one demulsifier work? If yes, we can proceed with the demulsifier formulation based on the working base demulsifier. However, if none of the demulsifier work, we need to further perform the literature review to further rectify the problem in case different chemistry is needed to resolve that kind of emulsion. Now, we have choose one candidate from Sarawak field, for us to test this demulsifier selection guideline. Okay, we can see here that this is the properties of the crude. The API is quite high, which is almost 40 degrees, and then wax content also high, and then the solid content is around 0.14%, and process temperature is around 40 degrees C. We can see here that based on the demulsifier selection guideline, when your wax content is more than 6%, you need to choose a higher RSN number, which is at RSN 21. For light crude at solid content of more than 0.1%, you also need to choose higher RSN demulsifier, which is RSN 21. So from this, we proceed with the demulsifier formulation, and we managed to develop the formulation where we combine the two types of RSN 21 resin alkoxylate demulsifiers plus ester and a little bit of amine, and we mix with solvent. And this is the results of the demulsifier formulation that you have tested to that emulsion from field B. Okay, it managed to resolve emulsion from 63% to 0%. Base NW still maintain 0.05%. And then we can see here also that the oil water reduced a lot also from 148 ppm to 85 ppm, which is about 43% reduction with the dosage of 20 ppm of demulsifier. Then we prove its effectiveness in the pilot testing at the field B itself. So based on this field trial, okay, we managed to compare the effectiveness against the incumbent demulsifier. So pre-trial baseline and post-trial baseline is actually based on the performance of the incumbent demulsifier. We can see that for the FD injection at 25 ppm, it managed to work better than incumbent demulsifier from the picture here. We managed to resolve emulsion to less than 1% and also managed to meet the PSNW of average 0.43%, and the clear water phase, from 672 ppm reduced to 155 ppm. In terms of the robustness, we would like to see whether are this demulsifier robust. So we test in other 4 emulsion from the 4 fields. We can see that besides field B, dual function demulsifier managed to resolve emulsion from other Malaysian fields following the similar dosage of incumbent demulsifier but with better water quality. It can be seen clearly from this image. However, this DFT has its own limitation whereby it needs to work only for API crude more than 21 degrees, asphalting content of lesser than 2%, and wax content lesser than 14%. As a conclusion, the study has managed to determine the relationship between the crude properties and demulsifier properties. Demulsifier formulation from resin alkoxylate-based demulsifier have been developed for treating oil and water emulsion in Petronas Malaysian field respectively. The formulations are form workable in static condition and also even at the pilot implementation. And last but not least, application of this demulsifier is robust since it also effective in treating emulsion from 4 other fields. So as a way forward, we would like to venture by testing this demulsifier in other fields to further reduce the chemical cost compared to the incumbent demulsifier, and also we would like to further commercialize our Petronas in-house product. With this, I thank you.
Thank you very much, Panor Hadira, for the nice presentation. Very, very informative and also technical. So thank you very much for the presentation. So let me check for the available question from the audience. Okay, so while still awaiting some questions, talking about the effective demulsifier, ordinarily one should expect that if the effective demulsifier and efficient demulsifier should be able to resolve the emulsion with water clarity. Thus, I think the dual purpose is probably unnecessary. So, what do you think about this?
You mean dual function, is it?
Yes, because
Yes.
I think the by dual function, you actually meant that it was able to resolve the emulsion, and also the the water quality was very clear. But
Yeah.
so I'm saying that actually these are the two observations that should be that are associated with the efficient demulsifier. So I just want you to probably just enlighten us on why this should now be a dual purpose. Is it really a dual purpose or just an efficient demulsifier?
So dual, from time to time, we enhance the facilities itself in the operation in the offshore, whereby more three-phase separator nowadays. So we need to really take care of the produced water separation itself. So right now the common application is by injecting the oiler and demulsifier, which is two separate chemicals. So with this new technology, what we can do is we can further reduce the chemical consumption, because the demulsifier, it also clarify your water phase. So that is why we would like to venture into this technology of the enhancement of this dual function demulsifier. Okay, so with the application of this guideline, demulsifier guideline, and also with the experience of demulsifier formulation, we've tried to help Petronas to further enhance this dual function demulsifier technology in the future. Yep.
Okay, thank you. Actually, the you have stated in your presentation that the guideline may not be applicable for crude oil of less than 20 degrees API, right?
If it's too heavy, it's not covered in our boundary data sets before when we developed this technology tool, but it's not a showstopper, whereby once we receive the data sheet or crude characteristic that have a lower crude API, we can further enhance the data set and also enhance the guideline as well.
Yes. Actually, that now leads me to the next question. In case you have a heavier crude oil, so what modifications will you rather make to the existing guideline for for the demulsifiers to be effective as well? Because heavy crude oils, they normally give very stable emulsions.
Correct. So for this guideline, we've only tested with three types of chemistry, demulsifier chemistries. So let's say if we receive a heavy crude in the future, so we can try to request or have some literature what type of demulsifier that suits to this heavy crude, and we will enhance base of using that specific chemistry and will enhance the guideline as well. Yeah, that's the
Okay.
plan for the future.
Okay. Now, going back to the RSN and also the HLB, which one of these two criterion, these two criteria, do you think is better to actually characterize the emulsifier or the surfactant? I mean, the emulsifier to better uh, formulate the best one to resolve emotion. So do you really think RSN is better than HLB, or so how do I mean, which one should be considered always?
So it's actually both is actually hydrophilic lipophilic balance of measurement. It's just that for the RSN is based on titration, so it's easier for you to determine the RSN value for each of the demulsifier. But for our case, the RSN number is we receive directly from the chemical vendor. Is in the chemical brochure itself. And sometimes also, but it seems that it's correlatable when it mentioned high RSN, the HLB also is a little bit is high, but still lower compared to the RSN. But it's still correlatable because it's the hydrophilic lipophilic behavior of your demulsifier surfactant. It's just that it's easier to measure RSN compared to HLB.
Okay, thank you very much.
Yep.
Actually, because this topic happens to be a very, very interesting one, so there is also one last question. You actually look at the effect of these demulsifiers on the wax content as well as asphaltene content. Did you also investigate the effect of resins content on the performance of these demulsifiers?
Okay, so resin we have the number of each resin component inside the synthetic crude, but somehow we know resin is not directly contribute to the stabilizing agent. So that's why we more focusing on the wax and asphaltene content, which we know is really stabilize the emulsion. But resin we know it on the other way around. It helps actually for when you have higher resin, it will not stabilize your emulsion because it usually not correlate with your asphaltene, right? So it vice versa with the asphaltene. Asphaltene is your stabilizing agent, but resin is not. So we are focusing more on the stabilizing agent, which is the solid, wax, and also asphaltene. So to study the effect of that three stabilizing agent.
Okay. Okay. Thank you very much. Thank you very much, Noradira, for the for sharing your knowledge with us this afternoon. So we really appreciate your time. So thank you very much. And I think that's about all for your session. Thank you once again.
Welcome.
So our next presentation will be by Hamed Fatah from Cotton University here in Malaysia. And the title of his presentation is Effect of Supercritical CO2 treatment pressures on clay-rich shale properties for CO2 storage application. So I will now leave the floor for Hamed Fatah to start his presentation. Over to you, Fatah.
Hello everyone, I am Ahmed Fatah from Curtin University, and today I'm presenting our paper entitled Effect of Supercritical CO2 Treatment Pressures on Clay-rich shale Properties for CO2 Storage Application. In today's seminar, I'm going to start first by giving you an introduction and a brief background about the study, explaining the research gap and significance, followed by the methodology, the results, and lastly the conclusion. Carbon capture and storage, or shortly known as CCS, is a reliable solution to reduce the greenhouse gas emissions into the atmosphere. Currently, conventional formations such as deep saline aquifer and depleted oil and gas formations are being considered to host CO2. However, in the last decade, considerable attention has been given to shale gas formation and consider them as a potential targets for long-term CO2 storage because of their wide availability, their ultra-low porosity and permeability, and because of their higher CO2 absorption capacity. So, utilizing CO2 in shale gas formations can also improve the shale gas recovery while simultaneously storing the CO2 and reducing the CO2 emissions. However, the injection of CO2 in the shale layers can cause geochemical interaction with the shale rock. In the long term, this interaction may result in mineral dissolution and precipitation, which will affect the efficiency of the CCS projects. When CO2 contact with the water, it forms the carbonic acid and causes major changes in the shale properties, the rock geometry, the fluid transportation, and the storage capacity. Therefore, it's crucial to understand the influence of CO2 injection on shale properties for better CO2 containment. The technical feasibility of the long-term CO2 storage in shales is mainly derived by the interaction between CO2 and the shale itself, and is highly affected by several factors, including CO2 injectivity, mineral composition, pressure, temperature, and the organic matter. Previous studies have shown that mineral dissolution and precipitation are the main factors affecting the shale properties. The alteration in shale mineralogy is influenced by the reactivity of shale to CO2 and also the presence of variety of minerals including clays, carbonate, and non-clay minerals. Clay-rich shales of particular interest can provide a good sealing integrity and storage capacity to host CO2 because of their high clay contents, which will promote higher CO2 dissolution. This behavior will cause, of course, a mineral precipitation and dissolution and may lead to major changes in the shale properties. Therefore, this work evaluates the possible physical, chemical, and mineralogical alteration in clay-rich shales and the implication on the overall storage capacity. This work will evaluate the impact of CO2 treatment pressures on the surface morphology and mineral composition. Also, will provide a quantitative analysis of the impact of CO2 treatment pressures on the organic and the inorganic functional groups, which was not addressed previously. Although there are several studies were conducted to understand the basic fundamentals of CO2 shale interactions, however, the knowledge on this subject is still evolving, and a number of further studies are needed. This diagram shows the methods that were used in these experiments or in this study. So before and after the CO2 experiments, several characterization methods were applied: XRD for mineral composition detection, thin sections for surface morphology, and FTIR for functional group analysis. This device, the static reactor, was used to treat the CO2, the shale samples with CO2. It consists of the reaction vessel and a supercritical pump to inject the CO2, and there is a pressure indicator and temperature controller to ensure that the injected CO2 in its supercritical conditions. The samples were collected from Eagle Ford shales, which is known with its high amount of clay minerals, and the bulk volume was crushed into powder to detect it or to analyze it with XRD and FTIR, and core shapes were used for thin sections. The samples were divided into separate portions to be tested at different CO2 treatment pressures. Moving to the results part. The first thing is the mineral composition. The table on the right shows the mineral composition of the samples before and after different CO2 treatment pressures. And we can realize that the proportions of quartz generally increase with increasing the treatment pressure, while the content of clays and carbonate minerals decrease. Specifically at high treatment pressures, the quartz content increased from 16.6% to 44.9 when the pressure increases to 24 megapascal, and this is confronted by a considerable reduction in the clay and carbonate minerals. And these variations in mineral composition are related to the ability of CO2 to dissolve and extract clay minerals as a result of forming the carbonic acid. So due to the shale heterogeneity, variation in XRD results up to 5% can occur, and that may cause some of the under or overestimated values of the mineral dissolution and mineral precipitations, as XRD may not accurately detect all the small changes in the minerals. This explains the fluctuations in dolomite and other minerals contents at 12 and 10 megapascal respectively. At low pressure, CO2 dissolution is usually weak, and that restricts the generation of hydrogen ions. Therefore, a low amount of clays was dissolved. Another reason for the reduction in the clay contents is related to the effect of clay swelling. Kaolinite and illite are considered or known as a non-swelling clays because of their low exchange capacity, and the increase of CO2 treatment pressure may result in increasing the absorption-induced swelling and cause clay hydration, which in the long term can lead to decrease of the porosity and permeability, and also reducing the storage capacity. The alteration in mineral composition plays an important role in the long-term CO2 storage injection in shells in terms of mineral trapping and CO2 storage. The alteration in shell mineralogy is the main factor affecting the changes in other shells properties, as we're going to see next in the
You are the
slides.
only one in
So there is
the
a strong
presenter
relationship
chat.
between the mineral composition and the alteration in the shell properties. The images on the right shows the thin section analysis for different CO2 treatment pressures, and the mineralogical changes detected by
Only your comment,
XRD
your
are
comment.
reflected
You
on
are
the
the
shell
one. You are
surface.
the one asking
However,
questions. You
it's
are the one
quite difficult to
answering yourself.
visually examine the changes on the surface morphology from thin sections. Therefore, histogram profiles were plotted to show the frequency of the non-clay contents in the shell sample before and after the treatment. So the histogram profile shows that there is an increase in non-clay minerals content frequency with increasing the CO2 treatment pressures, and this increase is due to the increase in CO2 absorption at high pressures, thus more clay minerals were extracted.
If there is no
We
question
provide
at
also a
all.
quantitative and qualitative analysis for the impact of CO2 treatment pressures on some of the main functional groups, including the aromatic, the aliphatic, and the hydroxyl functional groups. The FTIR spectrum on the right shows that after CO2 treatment, the produced spectrum shows similar peak shapes, confirming that the presence of the same minerals but with different concentrations. We divided the FTIR spectra into 4 regions to study the aromatic hydrocarbons, oxygen-containing groups, aliphatic hydrocarbons, and the hydroxyl structure. The aromatic hydrocarbons shown in the right shows that the 4H hydrocarbons reduced at low CO2 treatment pressures. However, increasing the treatment pressure accelerated the extraction of the aromatics on the shell surface, thus the absorbance percentage increased. This is related to the amount of dissolved CO2 in water, as the degree of hydration of hydrocarbon extraction increases with increasing the pressure and the temperature. The absorbance also for the CH bond showed a gradual increase with increasing CO2 treatment, confirming that CO2 can extract higher polar aromatics at high pressures. Studying the oxygen-containing groups is important because it gives an indication about the absorption as in terms of CO2 and also the overall CO2 storage capacity. The absorbance percentage of oxygen-containing groups increased gradually with increasing the treatment pressure, and that confirms the strong absorption capacity of CO2 in shells even at low treatment pressures. The aliphatic hydrocarbons, mainly the OH and the cyclohexyl group, showed a reduction after the CO2 treatment. However, the absorbance
So,
percentage of aliphatic groups is
if I
less
need
affected
to
at high
get some of
pressures,
these
and this is
papers,
related to
so
the increase in the extraction rate of the
who is in
aromatics
charge?
at
Who
high
is in
pressure,
charge of
which reduces the
the
extraction
papers?
rate of the aliphatics. And if we compare the aliphatics to the aromatics, the aliphatic contents are extracted easier due to the release of OH ions by the clays in the system. The hydroxyl groups represent the hydrogen-containing groups, and the formation of carbonic acid led to uh, reduce the intensity of the OH hydroxyl groups after the CO2 treatment. And similar to the aliphatic hydrocarbons, the overall contents of the hydroxyl groups are less affected at high pressures. When pressure increases, more hydrogen ions are formed. Thus, the strength of the carbonic acid becomes weak, and the mineral composition plays a significant role in
So,
forming strong or weak acid. Shells with high clay contents are more likely to form a strong carbonic acid compared to the shells with lower clay minerals. In summary, increasing CO2 treatment pressures had a minimum impact on the alteration of the aliphatic and the hydroxyl functional groups. However, further studies are needed to clarify the impact of the carbonic acid and the generation of the hydrogen ions. So what are the
yes.
implications of these changes in the shell properties on CO2 storage? The interaction between CO2 and shell mineralogy could be the first indication of the feasibility of a particular shell formation to host CO2.
Because
Clay-rich shells generally have a high
I'm
absorption
interested
capacity of
in
CO2, which is confirmed by the alteration and the increase in the oxygen-containing groups after the CO2
materials.
treatment. However, eagle-forward shells with their high clay contents may cause swelling in the long term, which reduces the CO2 storage capacity, and this point needs further investigation. In conclusion, supercritical CO2 treatment pressure is one of the factors that can contribute in altering the mineral composition, surface structure, and surface chemistry. And the mineral composition has an important role to define the changes of shell properties. The surface morphology of clay-rich shells is more affected by CO2 at CO2 treatment at high pressures due to the increase in hydrogen ions. The contents of aromatic hydrocarbons and oxygen-containing groups increase gradually with increasing pressure, while the aliphatic and the hydroxyl groups content shows minor changes at high pressures, which is related to the strength of the carbonic acid in the water. Thank you very much. That's all from me. And now we move to the Q&A session.
Thank you very much, Mr. Fatah, for the nice presentation. Okay, good.
Thank you.
Yeah, thank you for the very informative presentation. So let me check if we have some questions. Okay. Okay. The first questions goes thus. The CO2 storage is usually occurs at high pressure, right? CO2 is stored at high pressure. So, but can you please shed more light on how the high pressure is actually responsible for the reduction in the clay content and the increase in the quartz content. So how does pressure lead to increase or decrease in some certain minerals?
Hello, Dr. Adebayor, can you hear me?
Yes, I can hear you. I can hear you. Can you hear me also? Can you hear me? Can you hear me? Mr. Ahmed, can you hear me? Mr. Ahmed? Mr. Ahmed, can you hear me? Can you hear me? Okay, can you speak so that let me confirm if you can hear me or not? Muhammad Shafiq, please can you hear me? Basim, Ivy, I can see you raising your hand. Yeah, Basim, can you hear me?
Yes, I can hear you.
Yeah, I saw your hands up. It's like you wanted to ask a question.
No, just that I can hear you.
Oh, okay, it's all right. So we are we're actually waiting for. So we thought Mr. Ahmed will probably come up to probably listen to some of the questions. Okay. So I think if Mr. Ahmed is not I mean is no longer available, so I think we can go on to the next presentation by Mr. Bassem Said Mohammed from University Malaya, Pahang in Malaysia here.
Yes.
The title of his presentation is the synthesis, characterization, and evaluation of sterile acrylate, co-behenyl acrylate, that is SA-CoBA, copolymers as a novel PowerPoint depressant for Malaysian crude oil. So over to you, Mr. Basim, for your presentation. Thank you.
Assalamu alaikum wa rahmatullah. Bismillah ar-Rahman ar-Rahim. My name is Basim Al-Arabi. Today, inshallah, I will present small part of my PhD research, which is entitled Synthesis, Characterization, and Evaluation of Sterile Acrylate, Co-Behenyl Acrylate, Copolymer as a wax inhibitor of Malaysian crude oil. Let's start from presentation outline, which is consisting of introduction, methodology, result discussion, conclusion, and references. In the introduction, and as we know, in the recent decades, the world energy consumption and the crude oil demand have been increased dramatically, promoting mining and manufacturing companies to extend their processes into the gold regimes such as deep water offshore. Actually, this issue has become more dangerous for deep water offshore, wherever the temperature of the seabed is around 5 Celsius or less. And the main problems faced by the oil and gas industry in the most countries around the world is wax deposition on the pipe wells, which needs efficient and expensive method during production and or transportation of the waxy crude oil. Actually, wax deposition happens when the temperature of the crude oil drops down its wax appearance temperature. The wax start to precipitate from the fluid and started to aggregate into internal surface of the pipeline, thereby reducing the power, the flowability, and increasing the viscosity, and sometimes plugging the channel, as you can see in this figure. So to overcome this issue, so there are three remediation methods of the wax deposition, such as chemical method, mechanical, and thermal. For the thermal and mechanical, it's so expensive and needs to stop the production, while for the chemical method, no need to stop the production, and it's more cheaper than others. This slide shows us the methodology and the list of material that I used in my PhD research. This slide shows the experimental setup for synthesis of the PBD. And this apparatus consisting of 3-neck flask, magnetic stirrer, hot plate, thermometer, condenser, and nitrogen gas cylinder. This slide shows the chemical structure of the copolymer. This slide shows the characterization of the PBD copolymer, such as GBC, FTIR, NMR, XRD, and SEM. The evaluation of the PBD copolymer. So let's start from the pour point measurement. The pour point is a temperature point at which the oil loses its flow characteristic, and we measure the pour point by equation number 1. And the rheology measurement, the dynamic viscosity of crude oil has been calculated at differential rate and different temperature, and the degree viscosity and the degree of viscosity reduction, DVR, has estimated by equation number 2. This slide shows us the gold finger. analysis. Goldfinger have been used to evaluate the wax deposition as shown in figure 2, and wax deposit was scrubbed off from the surface tube of the Goldfinger and then weighted to estimate the paraffin inhibition efficiency, BIE, as shown in equation number 3. Result and discussion. This table shows us the physicochemical characteristic of Malaysian blank crude oil sample. For example, the viscosity of blank crude oil at 30 Celsius was 6.30 megapixel, and the burr point was 11 Celsius, and WAT was 28 Celsius. And the characterization of sabaco-polymer, GPC was measured, used to measure the molecular weight. The highest poly dispersity index was 1:1 at around 7.26 at 1:1 of the mass ratio. And as we can see, the molecular weight increased would increase the sterile acrylate content, and decreased when increased the vinyl acrylate content. And also this slide shows the FTIR analysis. So the highest peak at 2800 and 2800 and 2914 were attributed to the stretching vibration of CH2 and CH3 respectively, and the peak around 1731 is related to the C double bond O and is related to the carbonyl group. And as you can see here, this appearance of the absorption peak is around 1600. This means that the SA and BA have been already polymerized, and the peak around 719 and 720 is this related to the long alkyl chain of the CH2 group. And also this slide shows us the NMR analysis. The double bond have been located between the 5.5 and 6.5, have been disappeared as expected. This indicated that SA monomer and BA monomer have been polymerized, and the double bond transferred to into the single bond. And XRD analysis show us in figure 5 the typical peak of the copolymer in the crystalline form have been appeared at around 21.5 degree at all of the mass ratio, and this diffraction is due to the crystalline state of the long alkyl chain formed by SA and BA. Evaluation of sabaco-polymer on the burr point. The best mass ratio was 1:1. The best depression was 1:1, around from 11 Celsius to 2 Celsius at 1000 ppm and 5000 ppm. And the relation, this slide shows us the evaluation of the sabaco-polymer on the rheology measurement. So let's start from the effect of temperature on the viscosity. When the temperature of crude oil reduce, so the viscosity will increase dramatically. So this slide shows us the relationship between the shear rate viscosity and shear rate with shear stress. And we noted that at figure 7a, when the shear rate increases, the viscosity will decrease. But when the shear rate increases, the viscosity will increase dramatically. The highest DVR was around 89.7 at 1000 ppm and 5 Celsius. And the evaluation of the burr point on the wax deposition. So the amount of wax deposit of the blank crude oil was 1.1 gram compared with the amount of wax deposit treatment of the treated crude oil, which is successfully decreased to until 0.62. So the highest BIE was around 44%. Conclusion: the synthesized characterization and evaluation of copolymer as a novel bore point was investigated to improve the flowability and reduce the wax deposition of Malaysian crude oil at the lowest temperature. All the results indicate the copolymer sample had been different. Mass ratio was successfully synthesized, and the mass ratio 1:1 at 1000 ppm has a positive effect on the bore point depression and the most efficient reduction, and the highest BIE was around 44.14%. This is the reference that I use in my study. Thank you for your listening.
Basim, for the nice presentation. So very, very informative. And I can see that actually it involves a lot of characterization and evaluation studies as well. So I think the first question here is what actually informed the choice of the sterile acrylate and behenyl acrylate? Is there any unique characteristics of these two that make you to consider them for PPD?
Sorry, I didn't understand your point. Exactly your
Okay,
point.
okay,
Yeah.
okay. Let me ask you again.
Okay.
Why did you choose
It's A.
the sterile acrylate and behenyl acrylate as the pour point dispersant? So what unique characteristics do they have that
Okay.
made you to choose them as your potential PPDs?
Okay, thank you for your question. Actually, I have choose this SA and BA because based on the literature review. Okay, so I found that SA is very, very. They are using as BBD, but individual, not with using as polymer, not as copolymer, and also benyl acrylate. So in our contribution in my study is to synthesize the copolymer and using as a wax inhibitor. So that's why I choose this one, and no one use SA and BA and have been combination together in the previous studies or in the literature review.
Okay, okay, thank you. Now, I've also observed that you use different mass ratios in the formulations. So you use 1:2, you use 1:1, you use 1:3, you use 2:1, and you use 3:1. So did you also consider 2:2? And if yes, what is the result? If not, why?
Because actually I'm using mass ratio. So if 2 means like 1:1, you understand me, right?
Good. Okay.
Yeah.
Okay. Okay. Yeah. Yeah.
So
You're
that's
correct.
why I use mass ratio. It's not I didn't use volume ratio or I didn't use molar ratio.
Okay. Now, you said ratio 1:2 actually gave 91% flowability performance, and ratio 3:1 gave 88.5%.
Okay.
Now, the question is, what's actually responsible for the ratio 1:2 given 91%?
Again, please, your question.
Okay, okay.
Okay.
The ratio 1:2
1 to 2.
actually, yes,
Okay.
gave 91% flowability performance,
Okay.
and
For
the
the
ratio 3
for
to 1.
DVR, you mean?
ratio 3 to 1 gave 88.5%.
Okay.
88.5%
Okay.
flowability performance for ratio 3 to 1. Now, the question is, what is responsible for the higher performance for the ratio 1 to 2?
1 to 2. Okay. Actually, all of the mass ratio. Okay, because we are dealing with chemicals. Okay, all of the mass ratio have been minimized to wax deposition or reduce the wax deposition, and also to improve the flowability of Malaysian crude oil. So that's why we are using different mass ratio, because we would like to see what is the best performance. And if you return back to characterization of the GPC, you will find the highest bullet dispersity is 1 to 1. 1 to 1 of the mass ratio, which is the highest bullet dispersity. I think 7 point something percent. So the highest bullet dispersity means like more performance for the pour point, for the WAT, to reduce the pour point, and also to reduce the WAT.
Okay. Now, maybe let me ask the question again. Yes, I understand that your ratio 1 to 1, so has the highest. Just like you have explained, but when we talk about ratio 1 to 2,
Okay.
and ratio 1 to 3.
1 to 2 and 1 to 3.
Yes.
Okay.
Now, ratio 1 to 2 performs better than ratio 1 to 3, but ratio 3 to 1 also perform, given 88.5%.
Okay. So you will find when I think when we increase the content of vinyl acrylate, okay, which is bad, okay, you will find the performance is reduced. You understand me, right? The content of this ba, when we increase it more than sa, so we will find the performance is reduced a little bit. So, but I think the performance is same, not too much different.
No, I mean, you are 88.5 to 91. I mean, you still have about, maybe about 3% difference. So, I mean, so that is still considered something. Don't you think so?
Yes. That's
Okay.
different, yeah.
Okay. Now, did you compare the performance of this SA BE? Did you compare the performance with the conventional PPDs that's available in the industry?
Yes, I compare with the EVA BBD, but we find that SABA it's more performance than EVA, because the EVA it's commercial one, but the performance is not as much as it's not too much different between them, almost around 3% or 5%.
Okay, so in that case, so I mean, let's say, so what will be the selling point? What will be the selling point or the major advantage of the SA COBE over EVA, for instance? So how will you convince the oil industry to maybe discontinue with EVA and use the SA COBE? So what would that be selling point? Because
Yeah, I understand your question. That one, so you will see the what is the cost of the material.
okay.
You know, if you compare, so that's why we use SA and BA. So because it's less
Expensive.
no, it's inexpensive So and EVA, I think even EVA, it's not like too much expensive, but SABA, it's more less than EVA.
Okay.
And also SABA has long alkyl chain, and but EVA short alkyl chain. That's why maybe in the future they will using SABA as BBD.
Okay. Okay. It's all right. I think that's about all for now. So thank you very much,
Thank you.
Basim, for the presentation and for your response to those questions. So thank you very much. So, ladies and gentlemen, I think this is about the convenient point for us to draw a curtain today. We really appreciate your time and for being part of this presentation. So we hope to see you in some other events, hopefully before the end of Icoget. So thank you very much once again, and I wish you a very wonderful day ahead, wherever you are. Assalamu alaikum warahmatullahi. Good afternoon, good morning, and good afternoon, wherever you are. Thank you.